I'm Mara Downing, and I'm going to present the paper Symbolic Execution plus Model Counting plus Entropy Maximization equals Automatic Search Synthesis, created by myself, Abtin, Molavi, and Professor Lucas Bang. The program we created seeks to find optimal solutions to arbitrary search problems that are specified by the user. So, what is a search problem? A search problem is a problem in which there is an unknown target value which can be discovered through asking queries and receiving responses from each query that reveal more information about the target value. In our approach, queries are asked one at a time, and depending on the problem and the query, different amounts of information are revealed about the target value. A common example of this type of problem is the game Mastermind, where queries of 4 colored pegs are submitted to the game to determine the secret list of 4 colors. In terms of security, guessing passwords to try to determine the correct one is also a search problem, although in a well-coded password checker, the only information given is whether or not the guessed password is correct. Let's start with a simple search problem, the game of high-low. In this game, the player guesses numbers in a range and is told whether their guess is too high, too low, or equal to the target value. We can think through the process of this problem fairly quickly. If we guess a first query, Q0, that is too high, then we know the target must be between the lower bound and Q0, and thus we know our next guess should be between those bounds as well. The optimal way to solve this problem is by using binary search. However, not all search problems are as simple as high-low. Take, for example, Mastermind. If you haven't played Mastermind, the basic idea is that the target value is a list of 4 colored pegs chosen from 6 colors available. Guesses are also a list of 4 colored pegs, and the game informs the player of how many colors are the right color in the right spot, red, and the right color in the wrong spot, white. Players are typically given 10 guesses to determine the target sequence, although Donald Knuth determined that only 5 guesses are necessary in the worst case. Unless you've played Mastermind a lot, you probably don't know what to do if you get 2 white and 1 red as a response to a query. If you had to write a program to determine what to do next, it'd be pretty difficult. Given some time, you could write out which target values had been eliminated, but that too would be difficult. So, for our program, instead of asking users to specify how results should be handled, or to determine which possible targets are left, it is only necessary for users to write some code that determines, given a query and a target, what outcome should be given. In cases such as Mastermind, this process is much easier than determining the logic behind solving the game. Our program then handles choosing optimal queries and eliminating useless ones. So our program, given only the code for a search problem, can determine optimal queries and discover information about a target value. New knowledge is incorporated at each step, and future queries are made with the new knowledge in mind. We defined the domain-specific language GuiSE so that we could have control over a simpler environment for symbolic execution. It is a very verbose language, and the code here is the code for the high-low search problem we looked at earlier. You may be able to see some notable differences. Every variable is written with a type, and the return values are numbers instead of strings, since GuiSE does not have a string variable type. You may also notice that unlike Python, conditionals are not in the form if condition then do x, else do y, but rather if else, condition x, y. This is the grammar for the GuiSE language. It has assignments, functions, array accesses and writes, conditionals, and while loops, as well as integer and Boolean operations. Here is the overall approach our program takes. I will explain each step in more detail in the coming slides. Once the user has written a search problem specification in GuiSE, our program performs symbolic execution on the code to yield a set of outcome constraints. From there, we use model counting to determine the probability of receiving each outcome for each query. After that, Shannon Entropy is used to determine which query will yield the most information gain, and that query is chosen as the optimal query. That query is sent to the search problem specification, this time with a concrete target value. The outcome that is given by that query and that target value is then used to update the knowledge about the game, and the cycle continues. At each step, the knowledge is checked to see how many possible target values are left, and the search ends when the knowledge only allows for one possible target value. So the first step of this process is symbolic execution. The basic idea of symbolic execution is that all inputs to a program are given as symbolic variables, and at each decision point, a branch in the symbolic execution tree is created, and both outcomes of the decision are explored. When the program ends, each leaf of the symbolic execution tree contains information about the conditions required to reach that leaf, as well as the current values of all variables at that leaf. This example shows the symbolic execution tree of the game high-low. In some cases, branches are considered unsatisfiable and thus not explored further since their conditions are impossible to meet and there is no way the program can follow that branch. Also, although it does not happen here, if variables are changed or added before a decision point, their values are updated in the list of current variables for that node and all nodes below it. After we complete symbolic execution on the code of the search problem, the leaves of the symbolic execution tree contain the constraints on inputs that were required to reach that leaf, as well as the values of all variables at that point. We use this information to construct constraint outcome pairs by removing all variable assignments except for the final outcome, the value returned by the search problem specification. In some cases, the same outcome is associated with multiple leaves, so we combine their constraints in a disjunction. This constraint outcome pair is an example from high-low, where the range is from 1 to 8 and the query is lower than the target value. Our next step is model counting. Model counting is a process of finding the number of satisfying assignments there are for a logical formula, which will be 0 if the formula is unsatisfiable. For example, the simple formula x is less than 10 and x is greater than 5 has a model count of 4, since x can be 6, 7, 8, or 9. We use a program called Barvinock to compute these counts, and we're giving it the formulas from the constraint outcome pairs that we generated using symbolic execution. Model counting gives us the number of ways that each outcome can be produced by each query. For example, the query 6 in the game of high-low from 1 to 8 has 2 ways of being low, so a model count of 2. It has only 1 way of being equal and 5 ways of being high. Each of these model counts can then be divided by the total number of possible targets, in this case 8, to determine the probability that the query will produce each outcome. These probabilities are then used in Shannon Entropy to determine which query is the best choice. Shannon Entropy is an equation which measures the amount of expected information gain from asking a certain query, given probabilities of each outcome of the query. In the case of high-low, the set of probabilities are the probability that query Q returns low, the probability that it returns high, and the probability that it returns equal. A quick example of entropy is the weather. It is always sunny in Philadelphia, so if you're sitting inside on your couch, you can be certain that it is sunny. Standing up and opening your front door will not give you any information, so in this case, the entropy is 0. However, in Rochester, New York, there's a 50% chance of rain and a 50% chance of sun. So if you look out your front door, you can actually learn quite a lot, and the entropy value is 1. In a place like Claremont, where it is mostly sunny with the occasional rainy day, you could guess without opening the door that it is sunny, and most likely be right, but it isn't guaranteed, so you can still gain some information by checking. However, you don't expect to learn as much as you would in Rochester. So each query will have its own entropy value. In the game of high-low, we can again look at the query 6 as an example. Based on its probabilities of getting low, equal, and high results, its entropy is calculated at 1.299. By calculating entropy values for all viable queries, we can discover the maximum and thus choose the query with the highest expected information gain to submit to the search problem. This is an example of entropy values from the game High, Middle, Low, in which a query is two integers in a range, and the outcome is whether the target is above, between, or below those two integers. Lighter squares indicate higher entropy values. So with a range from 1 to 27, the optimal first query is 10, 18, as it splits the space evenly into 3 chunks of 9 elements. Back to the overall process of the program, symbolic execution is performed only once at the beginning, whereas model counting and entropy maximization are repeated every round, as they depend on the knowledge that is being updated at the end of each round. To speed up the program, we added a step between when the knowledge is updated and when new model counts are computed. This step is called existential quantifier elimination, and it filters out queries which are guaranteed to produce no new information. This step can also be handled in entropy maximization, as any query which can gain no information will have an entropy of 0, but since we can do it before even computing model counts, we can avoid a number of unnecessary computations. The essence of this filtering function is that we take the conjunction of the knowledge and a possible outcome for a single query, and the conjunction of the knowledge and the negation of that outcome for the query. By computing the conjunction of these two pieces, we can determine if both this outcome and something other than this outcome are possible for the query. With a disjunction across all outcomes, we determine whether or not the query has the possibility to produce more than one outcome, and can thus decide whether or not it is a useful query. If the query can only produce one outcome, then we can avoid asking it since we already know the result. Here we can see the actual interface used to solve these search problems. Inside of a Python live interpreter, we run our file. The program then asks for a search problem. It lists all of the available ones here, and in this case, I will choose pinpoint. Pinpoint is a search problem very similar to high-low, except that it asks for guesses in 2 dimensions rather than 1, and returns separate results for each dimension. It asks for some specifications, in this case, the upper and lower bound of the search space. For simplicity, I'll choose between 1 and 256. It has chosen the target 9394, and now it's running and finding the answer. We can see it is using the binary search strategy, and as it progresses, it's getting closer to each dimension's value. Here, we can see that it has found one of the dimensions, so now it can focus solely on finding the other one. Since it still has to make guesses for both, we can see it is choosing random options for the one that it's already found, since it can gain this exact same amount of information by guessing 2, or 93, or 100. When it finishes running, it presents the target value it has found, and reiterates the target from above so that the user can easily check that it has indeed reached the correct answer. For a more complicated example, we can look at bounding box. In this game, the target value is a rectangle in a grid, and queries are other rectangles within the same grid. If the query rectangle overlaps the target, it gives an outcome of 1, and otherwise gives an outcome of 0. In this example, we have a 10 by 10 grid. Before we start, green means overlap, red is no overlap, and this here is the target rectangle. The first query does overlap the target box. The second one, however, does not. This query here is interesting because it's trying to narrow down exactly what part of the first query was overlapped by the target. And the search continues. Here it's slowly defining the edges of the target box. And at this point, the target has been found, so the program reports that the target box we saw at the beginning is the only possible solution. Having attempted to play this game myself, it is very difficult, and I most definitely cannot solve it in this few steps. The full proofs are available in our paper, but in brief, we proved that the decision tree problem is polynomial time reducible to optimal search. Thus, true optimal search is NP hard, and so we chose the greedy approach to approximate this optimal searching without taking too much time or processing power. We also proved that the same query cannot be tried twice, as after it is guessed, it has an entropy value of 0, and thus with a finite set of queries, the program will eventually terminate. Since queries are eliminated when they cannot be used to gain any information, once there are no queries left, there is nothing left to learn about the target. So here we can see data from some numeric and array searching problems, including the high-low and high-middle-low problems mentioned earlier. The sorted array searching at the bottom is very similar to high-low, but it uses array accesses and thus takes more time on average to compute. A notable amount of this time is taken by the symbolic execution step. We can also use the average number of rounds to determine that these games are indeed choosing optimal queries. In the case of high-low, from 1 to 100,000, binary search should take at most 17 steps, which is the ceiling of log 2 of 100,000. So seeing an average of 15.6 rounds is good. These are search problems in which the target value is a pointer box in 2-dimensional or 3-dimensional space. We can see here the data from the game Pinpoint that I demonstrated earlier, which overall runs fairly fast. We can also see the game 2-dimensional bounding box from my earlier example, which does take a bit more time. The 10 by 10 grid takes about 6.5 minutes to solve on average. These search problems here represent trying to find a password in 2 different systems. Password checker is vulnerable to a segment oracle prefix attack, in which the time taken for the system to say that a password is incorrect can be used to determine how many characters of the prefix of the guess were correct. Repaired password checker, on the other hand, does not reveal any information besides whether or not the password as a whole was correct, and thus it takes many more steps to find much shorter passwords. These search problems here are modeled after common games, specifically Mastermind and Battleship. Mastermind, in this case, is exactly the same as the original game. Simple Mastermind only gives information about how many pegs are the correct color in the correct place. So, while the logic is a little simpler, you're getting less information each round, so it takes a few more steps to solve. Battleship is also simplified. It contains a single ship of size 3 rather than all 5 ships. We can again see that our approach is finding good solutions, as a full game of Mastermind takes on average 3.8 rounds, which is good, since Donald Knuth proved that you need a maximum of 5 guesses in the worst case scenario. It would be bad if our average was above 5. The first 2 search problems here, Counterfeit Coin and Horse Race, are modeled after logic puzzles. The counterfeit coin problem asks players to find which coin is either heavier or lighter than all of the others by balancing coins on a scale. Horse Race asks players to determine the ordering in which 5 horses will finish a race by only racing 3 at a time. The movie ranking puzzle is very similar to Horse Race, except it only allows 2 movies to be compared at a time. And some of these puzzles take quite a while to solve, you'll notice. So, in the future, we want to expand to a larger class of search problems, for example, ones with a dynamic target value. We also want to speed up runtime, since some of the search problems take much more time than we would hope. Further, we want to create an input language that is easier to write, since GuiSE is verbose and can get confusing quickly. Finally, our current approach only ends when all information about the target value is extracted, but it would be useful to also be able to solve search problems where only a subset of the target is needed to consider the problem solved. For example, if you only want to know the first, second, and third place finishers in horse race, it wouldn't be necessary to fully order all 5 horses. In our current ongoing work, we've actually made progress on some of these goals, including looking into ways parallel processing in key places can improve runtime, and creating interpreters to translate easier-to-write languages into GuiSE. Thank you for listening. Any questions?